So just a quick recap. We've been talking about approximating the area under a curve with a left-hand sum. That's a rectangular sum that uses rectangles that reach up to the left and touch the curve at the left-hand corner. But we can also do the same thing with right-hand sums. Take a look at this. The area equals the limit as n approaches infinity of this sum. This is the left-hand sum, right? The sum from I equals 0 to n minus 1 is a left-hand sum. But we can also sum from I equals 1 to n. The sum looks exactly the same, but the indices are different. We're going from 1 to n. This makes it a right-hand sum. It turns out that when n approaches infinity, this gives me the exact same limit and thus the exact same area. So you can calculate the area either using a left or right-hand sum. What we did before with the left-hand sum wasn't special. We could do it for the right-hand sum as well. Now, this idea of the limit that gives me the exact area is so important that we give it a name, and it's called the definite integral. So here's my definition of definite integral. If a function f is continuous, we define the definite integral to be, and it's read, the integral from a to b of f of x with respect to x is this limit as n approaches infinity of the left-hand sum, or this limit as n approaches infinity of the right-hand sum. Either of these limits will give you the value of this definite integral. Now note here I didn't specify whether or not f of x was non-negative. It just has to be continuous for this definition to work. But if f of x is non-negative, then this value will exactly equal the area under the curve. So let's go back to our original picture here. Remember this problem, the area under the curve. This area is exactly given by the definite integral if f of x is non-negative, and that's why it's so important. We don't have to approximate anymore. We can get the exact value. I want to talk about what the definite integral is. It's a really tough concept, and maybe one of the toughest concepts in all of calculus, but it's really important. And it answers the question, how do you find the exact area under the curve? Well, let's start with the area under the curve problem. Let f of x be a non-negative and continuous function on the interval ab. That's what we have drawn here. Find the area of the region lying beneath the curve y equals f of x, so below this red curve, and above the x-axis, so above here.
Okay, 5.2, definite integrals. We have here a picture of Sir Leibniz, and he is credited with being the founder of calculus, along with Isaac Newton, and so just kind of a cool picture. Moving on. Definite integrals, 5.2. What we're going to learn about is Riemann sums a little bit more. We're going to talk about them. The definite integral and computing definite integrals on a calculator. Nice. And talking about what kinds of functions are integrable. And the definite integral is the basis of integral calculus, just as the derivative is the basis of differential calculus. So we're going to talk a little bit more in-depthly now about integrals themselves. Quick review questions. I do want to go over a couple things here because we need to make sure we have reviewed some things from pre-calculus before we get into the meat of this calculus lesson. Hopefully we remember how to sum some things. So example down here, if I have this Greek symbol sigma and I have an n equals 1 on the bottom and a 4 on the top of n squared, that means that I'm taking 1 squared plus 2 squared plus 3 squared plus 4 squared. All right, and I'm adding those together. So make sure you recognize this symbol, sigma, right here. We did talk about that last year in pre-calculus. And I think that's good. So moving on. The solutions. All right. Hopefully that man talking to you made some sense, and we're going to talk a little bit more in-depthly about what he was talking to you about earlier. It says when we find the area under the curve by adding the rectangles, the answer is called a Riemann sum. That is named after a man named George Riemann, who came up with the idea of just separating these functions out into rectangles and then finding the area of each rectangle and adding them together. So we have this function here, a velocity function, which is 1 over 8 t squared plus 1, and I'm splitting this up into 4 subintervals over the interval from 0 to 4. The width of the rectangle is called the subinterval. The entire interval is called a partition. Subintervals do not necessarily all have to be the same size according to Riemann. Now, in the ones that we talk about, we do all make them the same size, but they do not necessarily have to be in order to be called a Riemann sum. If the partition is denoted by p, remember that's the length of the entire interval, then the length of the longest subinterval is called the norm of p and is denoted by that symbolism p with the brackets around it. As that longest one gets smaller and smaller, the approximation for the area gets better, and we've kind of talked about that. And so the limit, as the length of that longest subinterval goes to 0, is of the sum from 1 to n of, this is your height times your length, is a decent approximation for the area. So, this is called the definite integral. This is the official definition of the definite integral. The limit, as the longest subinterval goes to 0, of the sum from 1 to n of the height of this rectangle times the base of this rectangle is called the definite integral of f over a to b. If we use subintervals of equal length, then the length of the subinterval is delta x, which is b minus a over n, which you have seen you've seen already before with this man where he told you what delta x was. So we have the definite integral is then given by the limit as n approaches infinity, and remember this n is the number of rectangles we have. We've talked about that. If we continue to input more and more and more rectangles into this problem, then we're getting closer and closer to the area under the curve. So the limit as n approaches infinity of the sum, remember the sum adding the areas of all these rectangles together from 1 to n, of f of c sub k times delta x, and this is your height of the rectangle and this is your base of the rectangle. So I'm just summing together all of these areas. That's all this is saying. And I'm just trying to find the limit as the number of rectangles approaches infinity. Leibniz introduced a simpler notation for the definite integral because this looks pretty nasty. So let's just go into what the actual notation is that we talk about. What he did was he took all of this stuff here and he said, well, let's just notate it differently. This Roman S is the symbol for the integral. This A and B, those are your endpoints of your integral, the endpoints of your interval that we're looking at. F of x is the value of your function. Dx is the dummy variable, but in this case it refers to the length of your base. And you can kind of see where these all came from. F of c sub k correlates to the value of the function. That's the height. And I'm multiplying the height times the base, delta k, which refers to dx, or I'm sorry, delta x, which refers to dx over here. This integral from a to b takes the place of this notation, the limit as n approaches infinity of the sum of from 1 to n. Note that the very small change in x becomes dx. Alright, so talking about what every single part here means. The first part, that's our integration symbol. That's known as the integral of. That's how we start every one of these out. Our lower limit of integration is our a value. That's the lower part of our interval. The upper limit of integration is the upper part of our interval. The integrand is the function. That is the height of your rectangles. Dx just basically tells us what variable we are integrating with respect to. Now we need to talk about how to actually evaluate the integrals. Now that we know what all the parts actually stand for, we're going to actually evaluate some integrals. In section 5.1, we considered an object moving at a constant rate of 3 feet per second. And we knew that rate times time equaled distance, so 3t equaled d. If we drew the graph of the velocity, we saw that the distance was equal to the area under that line. So after 4 seconds, the object moved 12 feet because the area of this rectangle was 4 times 3. If the velocity varies now, so let's say we have a velocity of 1/2 t plus 1, our distance function would be the antiderivative of our velocity. And so what I've done is I've taken my velocity function, 1/2 t, I have just found what function would be the derivative, or what function's derivative would be 1/2 t plus 1. So I took a t and I added a 2, and then I took 1/2 and I divided it by 2 to get 1/4, and then if this was a derivative, its antiderivative would be t. Our constant is 0 since our position at time 0 is 0. So we don't have to worry about a plus c in this case. After 4 seconds, if I put in 4 into my antiderivative function, I would get 8. Well, notice that the area under this curve is also 8. We have a trapezoid here. Our base is 1. Our second base is now 3. Thus we got our 1 plus 3. Area of a trapezoid formula, 1/2 b1 plus b2 times your height. And your height here is 4. And notice that that answer ends up being 8. So we can find areas geometrically if we know shapes and we know that their area formulas are what they are. And we should see that they would match up to what I would get if I found my antiderivative of my velocity function and then just plugged 4 into it. The distance is still equal to the area under the curve. Alright, what if I gave you a velocity function that was 1/8 t squared plus 1? We could split the area under the curve into many thin trapezoids. This is similar to the problem we talked about when we were driving, and each trapezoid would behave like the large one in the previous example. So you can kind of see each one of these trapezoids that we've drawn in here. We can find the area of every single one of them and add them all together. It seems reasonable that the distance will equal the area under the curve. So if our velocity is the derivative of the position, here's my velocity function, 1/8 t squared plus 1. Therefore, my antiderivative would be 1/24 t to the third plus t. Let's talk about why. I would add an exponent, so that'd be t to the third, and then I take that third and I divide it 1/8 divided by that exponent. So that'd be 1/24 t to the third plus, and then the antiderivative of 1 would be t. So that's how we got our position function. If I put 4 into that, 4 to the third times 1/24 plus 4 is then equal to 6 2/3. The area under the curve is approximately 6 2/3. It's not exactly, because those trapezoids all have flat tops and not curved tops like a t-squared function would have. We will eventually start to use antiderivatives a lot more to find the area under the curve. That we'll get into in a little bit. A few more things. Area. We can have such a thing as negative area. If we would have a function that would go above and below the x-axis, we would have a net area. So the integral from a to b of f of x dx is equal to the area above the x-axis minus then the area below the x-axis. So area, when we were talking about it, is actually the net area. The integral of a constant if I have a function which is a constant, a horizontal line through C, where C is a constant on the interval from A to B, then the integral from A to B of f of x dx is equal to C times B minus A. That should follow here according to the diagrams. My height would be C, B minus A would be my length, height times length would give me the area of that rectangle. So C times B minus A. Same thing applies for negative functions also. It would just be negative C times B minus A. On calculators. If I asked you to find the integral from -1 to 2 of x sine of x dx, your calculator has an integral feature. So I'm going to pull up our calculator here and go to our home screen. You go to your math key, and if you scroll down to your math key, in your math key, there is something in number 9 called FNINT. Now, the book always says it's NINT, but in our case it's FNINT. So I'm going to hit enter, and then you type in your function, x sine of x, comma, and now we're going to make sure we know that the calculator knows with what respect the variable is, so that's got to be comma x, comma, and then you put your upper and lower limits, or lower and upper limits. So we would do -1, comma, 2, hit enter, and we'll get 2.043. Okay? If you go into y equals, you can also type in your function here, x sine of x. I'm going to set my window to be, let's just go -2 to 3 and do a zoom fit. Okay? And if I go to second trace, number 7, see your integral symbol of f of x dx? My lower limit it's asking for, so I will type in -1, enter. Upper limit, 2, are you ready? It actually shades it for you, and you can see that it is 2.04. Okay? All right. And I believe we are at the end. So come in tomorrow with any questions you may have, and we will discuss 5.2. See you, everybody.